Hi, welcome to the first of two videos dealing with Pascal's Triangle. The first video will deal with properties of Pascal's Triangle, such as powers, the Fibonacci sequence, and several other properties. And the second video will relate to Pascal's Triangle and the binomial distribution, including theory of probability. So let's go. The Binomial Expansion and Pascal's Triangle, part 1 of 2 videos. If we want to simplify the expression a plus b to the power of 0, what does it equal? It equals 1 because any base to the power of 0 is always equal to 1. What about a plus b to the power of 1? That equals a plus b because one of the index laws is that any base to the power of 1 is equal to the base. If we work out a plus b to the power of 2 by expanding brackets, and you can check with an earlier video that I did that covered expanding brackets, you will find that the expansion of a plus b to the power of 2 becomes a squared plus 2ab plus b squared. If we increase the power by 1, we can work out a plus b to the power of 3, or a plus b cubed. And we can write it in that form, and then by expanding brackets, we obtain what you can see there, a cubed plus 3a squared b plus 3ab squared plus b cubed. What about a plus b to the power of 4? Expanding in a similar way, we have the expansion shown, and one more, a plus b to the power of 5. Getting complicated, isn't it? Where is all this leading us to? Let's look at the coefficients of each term in each of those expansions. This is what I mean. The numbers in red are the coefficients of each term. Displayed in that form, that may not mean much, but let's display it in a way that makes a bit more sense or a bit more interesting. And there are the coefficients. They are written in a triangular display from top to bottom. This display is attributed to a very famous mathematician from the 17th century, Blaise Pascal, who used this to determine a lot of other properties of number theory and probability theory. Now in this display we can have as many rows as we like of values. This one has 10 rows. What if I wanted to work out the numbers that go in the 11th row, or any other row for that matter? Can you see a way of working it out? Let's have a look. Look at the top there. If we sum the numbers in the second row, 1 plus 1, it equals 2, which is the value immediately below it in the next row. If we look at the third row, if we sum the first two numbers, 1 plus 2, that gives us 3, which is the value immediately below in the fourth row. And if we continue that, 2 plus 1 is 3, 1 plus 3 is 4. So what can we conclude from that? Well, it seems that to work out the number immediately below, all we have to do is sum the two numbers immediately above in the previous row. And that, in fact, is the rule we can use to work out the value in any row. What we can look at now are some properties that can be found in Pascal's triangle of numbers. And the first one is a very well-known one, a very famous number sequence, which is called the Fibonacci sequence, or the set of Fibonacci numbers. 1, 1, 2, 3, 5, 8, and so on. Can you see a rule that tells us how to work out the next term in the sequence? Have you seen this sequence before? In fact, each term is the sum of the two previous terms. So for example, the first two terms, 1 plus 1, gives us the third term 2. The sum of the second and the third term, 1 plus 2, gives us the fourth term 3, and so on. Now the question is, does this sequence of numbers appear in Pascal's triangle? There's Pascal's triangle. Can you see where they might appear? The first term, 1, is there. Can you see where the second term is? There it is. What about the third term, 2? Perhaps the clue is that the numbers seem to be displayed diagonally. That means I'm shading them in a diagonal fashion. So the third term, 2, is the sum of what you can see there in that green rectangle, 1 plus 1. What about the fourth term, 3? There it is, 1 plus 2, and so on. All we do is take the sum of the numbers in each of those diagonals, and we can continue that indefinitely. I only have room to show what you can see there, but you can go on basically forever doing that. So that's a very well-known number theorem, or number sequence, the Fibonacci sequence. Here's another very well-known one, triangular numbers. There they are, 1, 3, 6, 10, 15, 21, and so on. Can you see a way of describing what's happening to get each term? Here's the clue. If you add 2 to the first term, you get the second term. Adding 3 to the second term gives you the third term. Adding 4 to the third term gives you the fourth term, and so on. Does that enable you to give me the next term after 55? What would it be? The next term after 55 will be 55 plus 11, which will be 66, won't it? Now, why do you think they are called triangular numbers? Do you think it's something to do with triangle shapes? Well, in fact, it is. Let's see that in a visual way. There we are. The first number, 1, we can just show using circles as one circle. The second term, 3, if we use 3 circles in the shape of a triangle, as you can see. The next one, 6, you need 6 circles, of course, to make that triangle shape, and so on. Okay, now that we've established what triangular numbers are, do they appear in Pascal's triangle? Yes, they do. And there they are. 2 diagonals of numbers, and each one contains the triangular number sequence. Okay, we've covered 2 number sequences, the Fibonacci sequence and the triangular numbers. Let's look at another one, another property of numbers, which is powers of 2. Now, what are powers of 2? They are all values where the base is 2. So the first one is 2 to the power of 0, which is 1. The next one will be 2 to the power of 1, which is 2, and so on. And you can see there in red, what they are is basic numbers, 1, 2, 4, 8, 16, 32, 64, and so on. Can we obtain those numbers from Pascal's triangle? There's our famous triangle again. Where do you think we might find those powers of 2? The first one, right at the top, the 1. 1 is of course the same as 2 to the power of 0. The next one, 2 to the power of 1, or 2. If we take the sum of the second row, 1 plus 1 is 2, and that's the same as 2 to the power of 1. What about 4? The sum of the terms in the third row, 1 plus 2 plus 1 is 4, which is the same as 2 squared. Can you see what's happening? We are taking the sum of the terms in each row to obtain the powers of 2. There's the next one, and so on. And finally, for our last row, 2 to the power of 9. But of course, we can go on forever working out powers of 2 if we can work out the sum of the terms in that row. Alright, so we've looked at powers of 2, and here's an unusual one, powers of 11. In a similar way to powers of 2, the powers of 11 are 11 to the power of 0, which is 1, 11 to the power of 1, which is 11, and so on. Where would they appear in our Pascal triangle? The idea is similar to powers of 2, where we took the sum of terms in each row. For the first value, 1, which equals 1 of course, that's the same as 11 to the power of 0, isn't it? For the second row, we're not taking the sum, but we're taking the combination of digits. So in the second row we have a 1 and a 1, which form the number 11. Can you see what's happening? For the next row, the digits 1, 2 and 1 form the number 121, which is the same as 11 squared, isn't it? The next row, 1331 is the same as 11 cubed, 11 to the power of 3. And for the fourth row, 14641. All seems fine at this point, doesn't it? What about the next row? It seems there's a problem. We have the numbers 1, 5, 10, 10, 5 and 1, and we know that we should be getting 11 to the power of 5, which is supposed to be 161,051. Do you think this method only works for up to 11 to the power of 4? In fact, it works for all rows, as I'll show you. So to show that the fifth row actually gives us the required answer, we will look at it in this way. Here are the numbers in that fifth row. Think of them as digits, even though, of course, the 10 is not a digit as such. Think of them as digits that we're going to break down in terms of their value. So, for example, if I had the number 56, that comprises 50 plus 6. That means 6 units and 5 tens. So, starting from the right, we've got our units, tens, hundreds, thousands, 10,000s, and 100,000s. So if we've got 1 unit at the right, we can write it as 1 times 1, which is 1. In the next column, we have 5 lots of 10, 50, 10 lots of 100, which is 1,000, 10 lots of 1,000, which is 10,000, 5 lots of 10,000, which makes 50,000, and 1 lot of 100,000, which is 100,000. So our answer as a basic numeral will be the sum of those numbers, which gives us the required answer. You can check one of the other rows, let's say 11 to the power of 6, using the same method just to convince yourself that it does work. So we've looked at patterns of numbers that can be formed or obtained from Pascal's triangle, and that basically is the end of the video. But what we will do in the second video is to look at in depth in terms of showing the binomial distribution and probability theory and how it applies. So see you in the next video. Bye-bye.